Today we're going to talk about chemical bonding and nomenclature. Let's just do a little bit review. Remember we had talked previously about pure substances and mixtures, and we had said that there's two different types of pure substances, elements and compounds. And then within elements there's two types of elements. There's atomic and molecular. Then within compounds, there's molecular compounds and ionic compounds. Molecular elements do not normally exist in nature with single atoms as their base units. They exist as diatomic molecules as their base unit, so two atoms of that element bonded together. And these elements here in yellow on the periodic table, those are elements that exist as diatomic molecules. So hydrogen's always H2, nitrogen's N2, oxygen's O2, fluorine's F2, chlorine's Cl2, bromine is Br2, and iodine is I2. And you do need to know this. Okay, let's talk about ionic compounds. Ionic compounds are compounds where one or more cations is paired with one or more anions. Remember, cations are typically metals and anions are nonmetals. Ionic compounds there's a complete transfer of electrons within ionic compounds from the metal to the nonmetal, and this is what causes the attraction. And then remember that ionic compounds have a formula unit, which is the smallest electrically neutral collection of ions, but they're part of a 3D array. Okay, let's talk about how to write formulas for ionic compounds. Since many elements have predictable charges, we can determine the formulas for many ionic compounds based on their constituent elements. So group 1, they form +1 cations, group 2 form +2, and then aluminum is always +3, zinc is always +2, and silver is always +1. And you need to know this. And then anions always have predictable charges. Group 17 forms -1, group 16 forms -2, group 15 forms -3, and silicon forms a -4 anion. Okay, so there's 4 steps to writing formulas for ionic compounds. First, you'll write the symbol for the metal and its charge, followed by the symbol for the nonmetal and its charge. So let's look at the ionic compound that forms when aluminum and oxygen. So the metal is aluminum, and its charge is 3+, so we write Al3+. Oxygen's the nonmetal, so we write O2-. The second step is to use the magnitude of the charge of each ion, so that's the charge without the sign, as the subscript for the other ion. So here you can see that aluminum forms +3, so that means the subscript for oxygen is going to be 3. Oxygen forms -2, so the subscript for aluminum will be 2. The third step is, if possible, reduce the subscripts to give a ratio with the smallest whole numbers. We can't reduce Al2O3 further. And then 4, check to make sure the charges cancel, because remember we want to have a neutral formula unit. So here, the cations, we have 2 times +3, so that's +6. Our anions, we have 3 times -2 is -6, so the charges cancel, so we're good. Let's look at another example. So we're going to write the formula for the ionic compound that forms between magnesium and oxygen. So step 1, we write the metal Mg2+, and then the nonmetal O2-. The second step is we swap magnitude of the charges for subscripts. Step 3, to reduce the subscripts, we need to divide both by 2. So we can take Mg2O2, divide that by 2, and we get MgO. And then the fourth step is we want to make sure that charges cancel, so we have one cation with a +2 charge, and anion with -2 charges cancel, so we're good. So just the thing to point out is that, again, we want our formulas for the ionic compounds to be as simple as possible. So if you can reduce the subscripts after doing the charge swap, then you need to do so. Okay, let's talk about polyatomic ions. Polyatomic ions are ions that are composed of a group of atoms with an overall charge. Here's some, like a chart of some common polyatomic ions. So they're like a little unit of charge, but the atoms within the polyatomic ion are covalently bonded. But polyatomic ions always stick together. You don't need to memorize these, but you do need to be familiar with them. You can have, I have a chart of the polyatomic ions on D2L under this week's module. In the quiz, there's like a quiz 4 folder that you can use that when you take quiz 4, and in there are polyatomic ions and their names. So you just need to be familiar with them. You need to be able to look at a molecule and recognize that there's a polyatomic ion there. That's it. Okay, so let's talk about how to write ionic compounds with polyatomic ions. So the first step is to write the symbol for the metal ion followed by the symbol for the polyatomic ion. So same as before. So sodium and sulfite. Let's look at that. So sodium is Na plus, sulfite is SO3 2 minus. Then again, you use the magnitude of the charge on each ion as the subscript for the other ion. So we have Na2 SO3 1. Check to see if the subscripts can be reduced. You cannot further reduce the subscripts, so the formula is Na2SO3. And then we confirm that the sum of the charges cancel. We have 2 cations with +1, 1 anion with -2, so our charges cancel. Okay, let's look at aluminum and hydroxide. So for the first step, we have Al3 plus and OH minus. Step 2, we swap the magnitudes of the charge for subscripts. And here I just want to point out, so if you have just one polyatomic ion, so here the subscript's 1, which of course we drop, you don't need parentheses around the polyatomic ion. You don't do that. But here we have 3. So what you have to do is you need to put a parentheses around the polyatomic ion and then write the subscript outside of the parentheses. But again, we only do this if you have more than one of those polyatomic ions in the molecule. Then the third step, same. We can't reduce this further when we check our charges, and our charges cancel. All right, let's talk about how to name ionic compounds. So there's 3 different naming sets. So the first one is metals with predictable charge. So how we write the names for these is we have the name of the cation, the metal, then the base name of the nonmetal with the suffix "ide." You do not need to specify the charge of the metal because, again, these metals have predictable charges. Their charges don't change. So NaCl, Na is sodium, Cl is chlorine. So the name is sodium chloride. CaBr2, calcium bromide. Zn3N2, zinc nitride. You can see here's some common anions. And again, you just get rid of the suffix in their name, and then you replace it with "ide." So you have fluoride, chloride, bromide, iodide, oxide, sulfide, nitride, so on and so forth. And then when you're going back from the name to the formula, which you'll need to be able to do too, remember we can figure out the formula from the name because we know the charges of the metals and the charges of the anions. Okay, now we're going to talk about naming ionic compounds that have metals with unpredictable charge. So some metals that form more than one type of ion and their common charges, here's just a chart of this, and this is not exhaustive at all, but it's just meant to show examples. And basically it's, if I go back here, here's what I listed for cations and their charges. These are the predictable ones. Everything else that is a metal is non-predictable charge. So that's basically the transition metals. They can form more than one charge because of their d orbitals. But again, here's some examples: chromium, iron, cobalt, copper, tin, mercury, lead. Here's the symbol for the ion. So you can see chromium can form Cr2+, Cr3+, and there's more than that. Iron, 2 and 3, cobalt 2+, 3+, so on and so forth. Then how we write their name is we write the name of the element, and then in parentheses we put the charge in Roman numerals. So chromium 2+, excuse me, the name is chromium 2. That's how we say it, and we write it chromium with the Roman numeral 2 in parentheses. Chromium 3+ is chromium 3. Iron 2+, iron 2. Iron 3+ is iron 3. Tin 4, so on and so forth. So you have to put the charges in parentheses again because all these elements can form multiple charges. So we can't determine the charge just by looking at what element it is like we could with group 1 and 2 and silver, zinc, and aluminum. Because the charge of the cation is always the same, we have to specify the charge in the metal's name. So how we name these these ionic compounds, we put the name of the cation, the metal, then the charge of the cation in Roman numerals in parentheses, and then the base name of the anion, the nonmetal, plus I. So it's exactly the same as before with the predictable charges, except that we have to include the charge of the cation in parentheses. So if we look at this example, we have FeCl3. That name is iron 3 chloride. So you have to determine the charge of the metal from the chemical formula of the compound. We'll always know the charge of the anion because remember, anions always have predictable charges. So we can determine the charge of the metal from the charge of the anion. So here, chlorine we know forms -3. We have 3 of those, so we have a -3 charge from the chlorines. So iron must have a +3 charge for the charges to cancel. That's how we get iron 3 chloride. If we look at CrO, well, oxygen's -2, so chromium must be +2, so we get chromium 2 oxide. Okay, now let's talk about naming compounds with the polyatomic ion. So we name these the same as other ionic compounds, except we use the name of the polyatomic ion wherever it occurs. We don't have to change any suffixes. So KNO3 is potassium nitrate. K is potassium, NO3 is nitrate. You can also have 2 polyatomic ions in one ionic compound. So here's ammonium nitrate. Ammonium is NH4+, nitrate is NO3-. Here we have iron 2 oxide. Here we have manganese 2 nitrate. And again, you don't have to memorize the names of the polyatomic ions. You can use the chart on quizzes and tests, but you do need to be familiar with them, and you need to be able to look at a molecule and say, oh, that has a polyatomic ion in it. And basically for ionic compounds, your clue will be you don't have a binary compound. By that I mean you have an ionic compound with more than 2 elements in it. Okay, let's talk about molecular compounds. So molecular compounds contain covalent bonds, which means they share electrons. And these are generally between 2 or more nonmetals. Remember, in ionic compounds, you have the metal, which gives up an electron to the nonmetal. So there's a complete transfer of electrons. Here, there's no transfer of electrons. There's no ions being formed. They just share the electrons. Okay, here's how we name molecular compounds. It's pretty straightforward. So you take the prefix, name, so you have the prefix, then you have the name of the first element, then prefix, and the base name of the second element plus ide. So same thing as before, chloride, fluoride, so on and so forth. And here are the prefixes. So mono's 1, di's 2, tri's 3, tetra's 4, so on and so forth. And again, you don't need to memorize these prefixes either. They're also included on that packet on D2L for your quiz. Excuse me. Okay, here's some examples. So what we do is, we have the name of the first element. So here it's carbon. Then we have the same name of the second element with ide, oxide. And then we have to put prefixes in. We don't, if the first element just has 1, so its prefix would be mono, we don't include that. But the second element will always have a prefix, even if it's 1. So here we have carbon dioxide. We have 1 carbon and 2 oxygens, dioxide. N2O, we have 2 nitrogens, so we have dinitrogen, just 1 oxygen, monoxide. If your element starts with a vowel, you just drop the vowel off of the prefix. Here, CCl4 is carbon tetrachloride, N2O4 is dinitrogen tetraoxide. Again, this is carbon tetrachloride, not monocarbon tetrachloride, because we don't include the prefix mono on the first element. So these are nice because it's pretty easy to go back and forth between name and compound. You don't have to figure out any charges, anything like that. the name tells you exactly how many of each element are in that molecular compound. Okay, finally let's talk about naming acids. So acids are molecular compounds that produce H plus ions when they're dissolved in water. So for example, HCl and then AQ in parentheses is hydrochloric acid. This AQ in parentheses indicates that it's dissolved in water. You absolutely must write AQ in parentheses following the acid's molecular formula, or else you're not saying that that's an acid. By definition, an acid has to be dissolved in water. HCl without the aqueous is a gas called hydrogen chloride. It's not hydrochloric acid. So you will be graded on this. You must put AQ in parentheses after the acid's molecular formula. Okay, so there's 3 different naming systems for acids. The first we'll talk about is naming binary acids. So that's a hydrogen and a nonmetal. And they're pretty straightforward. So the names are hydro plus the base name of the nonmetal. And then ic is the suffix, then acid at the end. So here we have hydrogen and chlorine. So we have hydrochloric acid. And it's chloric because we take the base name, and ic will be the suffix. Here we have hydrogen and bromine. This is hydrobromic acid. Hydrogen and iodine, hydroiodic acid. Hydrogen and sulfur, hydrosulfuric acid. So on and so forth. So this is if you have hydrogen and a nonmetal. Then there's oxyacids. So oxyacids are acids that contain oxyanions, which are listed in the table of polyatomic ions. So it basically is a polyatomic ion with oxygen in it. So the base name of, so how you name these is you take the base name of the oxyanion, and then you're going to add some suffix and then acid. Excuse me. The suffix depends on the name of the oxyanion. So if the original name ends in "ite," the suffix is us, O-U-S. If the name ends in "ate," then the suffix is ic, I-C. So you can see here, if we have nitrous, or sorry, let's start here. So if we have nitrite, so we look at this, the polyatomic ion is nitrite. So since it has the suffix "ite," we change it to us, and we get nitrous acid. Here, this acid, the polyatomic ion, is nitrate. So we change the "ate" to "ic," we get nitric acid. Here we have sulfurous acid, sulfuric acid, chlorous acid, chloric acid, acetic acid, carbonic acid. So you look at, again, you look at the name of the oxyanion. If the name ends in "ite," then we change the suffix to us. If the name ends in "ate," we change the suffix to "ic." So here, H2SO4, the oxyanion is sulfate. So the suffix changes to "ic," and we have sulfuric acid. Here we have H2SO3. The oxyanion is sulfite. So the suffix changed to us, so we have sulfurous acid. Here we have HNO2. The anion is nitrite, so the suffix changed to us, so we get nitrous acid. And here we have HC2H3O2. The polyatomic ion is acetate, so the suffix changes to "ic," and we get acetic acid. Here's just a summary of nomenclature. So if we have carbon, if we have C and O, that's a molecular formula. So we say carbon monoxide. We have the name of the first element, the suffix, and then the name of the second element with the "ide" suffix. CaF2, this is ionic. There's only one type of ion, calcium can only form +2, so we just call it calcium fluoride. We don't include the charge. Let's skip down here. We have FeNO3, 3. It's ionic. There's more than one type of ion, and we have a polyatomic ion. So here we have iron 3 nitrate. Nitrate's the name of the polyatomic ion. It's iron 3 because NO3 has a -1 charge. We have 3 of those. We have to cancel that, so we have a +3 charged iron. If we look at here, this is HF. This is an acid. It's binary, so we have hydrofluoric acid. Here we have HClO4. It's an acid with an oxyacid that ends in ate. So we have perchloric acid. Here we have H2SO3. This is an acid. It's an oxyacid. The oxyanion ends in ite. So you have sulfurous acid. So I just want to recommend to you that on D2L, I posted this packet, and the packet has all of the nomenclature rules and a lot of rules that we'll be talking about next week too. And it's really good summary of the rules. And then it has a ton of practice naming problems. So I strongly suggest you go through and you do all these practice naming problems in the packet. I also posted the key online. And then we'll finish the packet with next week's material.